Okay, so welcome everyone to the second colloquium talk of the Trust Lab. I'm very happy to have Adithya Vadapalli. He's a postdoc at University of Waterloo with Ian Goldberg. Prior to that, he completed his PhD from Indiana University Bloomington under the supervision of Ryan Henry. His PhD thesis was on distributed point functions and their applications to secure multi-party computation. His primary research interests lie in privacy-enhancing technologies, works on both coming up with cryptographic protocols and building secure systems. And today he'll tell us about DPFs, or distributed point functions. So, go ahead.
Thank you very much, and I'm very happy to be here and talking about privacy-preserving collaborations and how distributed point functions can come to the rescue over here. So let's start talking about the internet. And the early pioneers of internet really had a grand vision about it. They had thought about creating this whole world of where people can enter without privilege or prejudice, and of like race, economic power, or status of birth, and it's like a level playing field is what everyone had envisioned. It was considered people considered internet to be a great equalizer, as some of these headlines tell you, and as the decades passed, this trust, or this whole promise which people thought internet give seems to be broken in some ways. So the question about can we put all our trust in the government has been answered pretty well with the Snowden revelations, for example. And even the question of can we put all our trust on big corporations? Well, we have had cases of, say, Cambridge Analytica or something. And if you have been following the news in the past 10 years, you know that the answer to that question as well is no. At the same time, our reliance on internet has grown rapidly, right? We have started shopping. We used to shop like this, and now we shop like this. From watching movies or entertainment like this, a vast part of our entertainment now is like this. At the same time, these benefits also come with great risks and great privacy threats. And these are a few cases that I picked up from the local news in the past 10 years. And there was a case of Target, which is a major supermarket in the United States, and they figured out that a teenage girl was pregnant before her father did. And how did they do that? The way they did that is that they noticed changes in her purchase patterns, and those purchase patterns led them to believing that she is pregnant, and started giving them targeted advertising related to pregnancy material. Similarly, there was a very famous case of TiVo thinking that a journalist is gay just by seeing their consumption history on the television. And there have been several cases of algorithmic discrimination where similar job applications have been submitted, one by one particular race and other by other, and it has been seen that there is a clear algorithmic discrimination that exists. So we have seen that. So this entire move to the internet and this digitization in many ways is a double-edged sword, right? There is great personalization when we get amazing recommendations, data-driven creation, fraud detection. For example, if you're using your credit card and your credit card company quickly detects that if you've made a huge purchase somewhere in a location where you are not supposed to be, it quickly detects it. And all these things are great. At the same time, it comes with these negative effects like the chilling effects, algorithmic discrimination, erosion of democracy, and creating echo chambers and so on. And there have been several ways in which we have tried to tackle this problem. And I somehow vision it as three main ways in which we have tried to solve this problem. One is something like putting your trust in a secure hardware and doing these computations or or sensitive computations using a secure hardware like Intel SGX, or using homomorphic encryption, or distributing your trust among several parties. Each of these has different pros and cons. For example, something like an Intel SGX would be extremely fast computationally. At the same time, it is still a question about how much can you actually trust this hardware. On the other hand, trust on homomorphic encryption is way more natural, as you are trusting a mathematical problem that is believed to be unsolved. At the same time, it comes with the problem that scalability of these instances is less because they are inherently much slower. And then you have this distributed trust, which I'm going to talk about in this talk, where you are distributing the trust among several parties. And typically there is something called a non-collusion assumption that if none of these two, if not many of these parties interact with each other, you should be fine. So we'll be talking about distributed trust. And the agenda of this talk would be first to talk about this dichotomy of the internet being a great place where you have all the benefits, at the same time also our privacy threats. So there is this tussle going on, and then about the broken promise of the internet, and a little bit about the future work. So let's start this. Let's start with the first part, and I'll talk about I'll start with Netflix as a use case. We have a protagonist, Bob, who watches a particular movie, let's say Invictus on Netflix, and is very happy with it. Next day, he watches another movie, Shawshank Redemption, he's chilling and he's very happy. And then Netflix figures out that this guy likes movies in the drama genre, and perhaps movies featuring Morgan Freeman in it. And it recommends Bucket List, which he enjoys, and he gets recommended, say, 12 Angry Men, and his life goes on very well. But the problem is that Netflix has learned what Bob watches and Bob likes. So the question that we ask is, can we build a media delivery system that can give the same personalized recommendations that we were getting earlier, but at the same time, can we hide the consumption history from the platform? And the answer to that is yes. And what we'll be using is PETs, not these kind, but privacy enhancing technologies, namely private information retrieval, distributed point functions, and secure multi-party computation. So a quick detour into hiding the consumption history. So what is the most simplest way to hide consumption history? For example, if we are in the same Netflix use case, what you can say is that, hey, I want to watch a movie. And what Netflix does is that, okay, just download the entire our Netflix catalog and watch whatever you want. Now, this is great in terms of hiding the consumption history, but it requires you to download the entire database, and that's, of course, not practical. So a very informal definition of private information retrieval is that users want to download something from a database without the servers knowing what they downloaded. At the same time, we want to have a caveat that the amount that you download should be reasonable. So now let's try to look at the database, that is what we are downloading from, slightly more formally. And typically in these information theoretic PIR protocols, that is information theoretic private information retrieval protocols, we represent the database as a matrix. And typically what we want to download is a certain row from this matrix. If we want to follow the Netflix analogy, consider the I* row as the movie that you want to download. Now, before we look at a non-private way to do it, before we look at a private way to do it, let us see what is a non-private way to do it. It's pretty straightforward, is that you take a vector, which is 0 everywhere except at the I* index, and you take a dot product of this vector with this matrix, and you should get the record that you are looking for. But the problem, of course, is that this leaks the index I*. So the non-private way is to do something like this. Now, how can we prevent the leakage of I*? So this is the first step towards it. What we do is that we replicate this database among two servers. And now we assume that these two servers will not interact with each other. And now once we have this assumption, what we can do is that we send a completely random vector to one of the servers. And we send a random vector XORed with the standard basis vector at I star to the other server. Now, from the point of view of each of these servers, they have just received a random vector. And what they return back is what they were returning back earlier in our non-private case, that is a dot product of what they received and the database. But now what the user receives back has an interesting property, because although these vectors Q0 and Q1, which they sent to the two parties, seemed completely random to the two servers, they're not actually random. They have this nice property that they XOR the standard basis vector at I star, and that's why they can simply reconstruct what they received and get the row that they were looking for. Now this is great. This is achieving our first task of private information retrieval, but there is still a problem, right? The problem is that the upload costs are huge. Now consider, for example, a Twitter database, and now you want to download a certain tweet privately. You would be sending vectors to the length of the database in order to download something of tweet size, because like if you recall our vectors Q and Q1, they were of the height of the database. So that is not ideal. And this is where distributed point functions come into picture. Before we look at distributed point functions, a very quick definition of what point functions are. Point functions are functions over a certain domain, which take in two main parameters, and they output to 0 at every point in the domain, except at one special point, which we call I star, where they output a special value, we call it M. And distributed point functions are a very succinct way to share these point functions among two or more parties. Already you must be noticing that these point functions and sharing them in a succinct manner has great advantages, because if you evaluate this point function over the entire domain and set M to 1, for example, you're basically sharing the standard basis vector. So what are distributed point functions? These were introduced by Gilboa and Desai in 2014, improved upon by Boyle, Gilboa, and Desai in 15 and 16. And they have two main algorithms associated with it. One is a generator algorithm, which the client runs. And the generator algorithm takes in a security parameter lambda, the special index I star, that is the only index where we want the point function to be non-zero, and M, the value that we want, the non-zero value at I star. The generator algorithm, after taking in these parameters, gives out two DPF keys, namely DPF0 and DPF1. And the client then sends these DPF keys to the two servers, P0 and P1 respectively. Then there's a second algorithm associated with DPFs known as the eval algorithm. The eval algorithm takes in as input an index from the domain of the point function and the DPF key. The output of the eval algorithm is interesting, that the output of the eval algorithm looks completely random to both P0 and P1. However, it has this great property that it XORs to 0 at every point in the domain of the point function, except as you expect at the point I star, where it evaluates to M. Now, we represent the function evaluating the DPF over the entire domain with eval full. And naturally, eval full of a DPF is a vector, which is basically eval of the DPF at all the points in the domain of the function. And once again, naturally, eval full of DPF0 and DPF1 would XOR to the standard basis vector at I star scaled by M. Now, let's come to the second important ingredient that we would be using, and this is called secure multi-party computation. I mean, so far we have only seen how we can download stuff privately, but we haven't solved the other problem of getting recommendations from these privately. And that problem is, and in order to tackle that problem, we look at secure multi-party computation, which is a well-known tool, and the rough definition is that you have n parties, all have their secret inputs. We call them W1 till Wn, and they want to evaluate a function f, which takes in these parameters while keeping their W's a secret. So they run a particular protocol in many cases, and they all learn the function f or the shares of a function, however we specify this protocol. And there's a very important notion of T privacy, which is very important, especially in this distributed trust settings. And T privacy means that all this works unless no more than T parties collude with each other. So if there is a collision of more than T parties, then our privacy will break. So it is under these assumptions, these trust assumptions, that secure MPC in this setting works. Okay, and there's a final thing of, I've been talking about secret sharing. I just wanted to define it once. So if you have a secret X, and if parties hold X0 to Xt such that they all XOR to X, we call them as XOR shares. And if they all add up to X, we call them as additive shares. Now let's get back to the problem. So our first task was to download things privately, and there have as we might have seen, DPFs seem extremely nice in fetching these records privately, and there have been several DPF-based PIR protocols, and we picked up one of these from the PETS paper, and these HHPIR protocols are actually so fast that you can even stream videos privately. However, they come with a very strong non-collusion assumption. The non-collusion assumption basically states they are one private, in the sense that no two parties can collude with each other. So at the cost of such a strong non-collusion assumption, what we get is extremely fast PIR. But now we have to provide recommendations. And what we do is that we use secure MPC on top of these DPF-based PIR queries. And the recommendation system algorithm that we use is the most popular recommendation system algorithm that exists, known as the collaborative filtering. And we don't need to get into the details of the recommendation system algorithm, except that we need to look at what are the computations that we need to perform, and we need to see how we can perform these computations privately. So there is a notion of something called user and item profiles. And so these are, so if you have M users and M items, we have these user and item profiles, which are an N cross D and M cross D matrices. And D is a certain dimension, which is a parameter that is chosen heuristically. And then after a user I has downloaded an item J, then the user and item profiles are updated. That is, if a user I has downloaded item J, you update the ith user profile and the jth item profile, and they are updated as follows. That is, you take the dot product of the user and item profile, multiply it with the jth item profile and add it to the user profile, and similarly. And then you have to normalize the user and item profiles. And the way it works is that the dot product of UI with VJ gives the propensity of user I liking item J. And this is one of the works that I'll be presenting, which appeared in PETS. And we presented a system called Persona, which is a 4-party secure MPC protocol to do collaborative filtering. And it is 4-party with 1 privacy, in the sense that our assumption is that no 2 parties collude with each other, which is a rather strong assumption. And the way it works is that you have these 4 parties which are required for our secure MPC. you can have more you can introduce more parties which can make the PIR more efficient, but the secure multi-party computation requires 4 parties, and they have 2 additive shares of the user and item profiles. Now, just by looking at the distribution of the way user and item profiles are distributed among these 4 parties, you would notice that it is indeed too private, because if any of the 2 servers collude with each other, for example, these 2, you would basically learn the user and item profiles. And the way the PIR protocol works, there is no way any 2 can talk to each other. Now, the way it works is that you send these DPF queries, you get back, you download the record that you wanted to download, and then there is a secure multi-party computation using these DPF queries as the input, and then the user and item profiles are updated, and you get further recommendations. So what are the technical ingredients that went through? We used distributed point functions to do PIR. Then we updated the user and item profiles, and in order to do that, we had to build these gadgets called 4-party multiplexers and demultiplexers. And then we had an efficient normalization protocol and an extremely efficient comparison protocol. In this talk, I'm going to talk about one of the technical ingredients, which is the 2-party demultiplexer, which I think was the most challenging. And the 2-party demultiplexer basically allows us to do this operation of updating the item profiles. In order to do so, we look at how DPFs are constructed. We look at the problem in hand, and we'll see the solution. So the way DPFs are constructed, or at least the most efficient version of the DPFs are constructed, is by something called a length doubling PRG. A length doubling PRG takes in as an input of length lambda and spits out an output of length 2 lambda, which is pseudo random. And now you can treat this output as 2 children of the node of size of lambda bits, and these PRGs, of course, have the property that if x is equal to y, then x0 is equal to y0 and x1 is equal to y1. That is, the left and right children are same if you have the same output, if the same input to the PRG. And if they are not equal, with a very high probability, you can assume that the left and right children are not equal. And now comes the important part about how the DPFs are constructed. P0 and P1 start with 2 random seeds of length lambda, and they construct this binary tree just by doing this length doubling PRG. And the number of leaves in this binary tree is equal to the size of the database. Now, the property that you want is the DPF tree to look something like this. What do I mean? You want that the tree should be equal everywhere except at one location, which is the location where you are querying. But just by applying this length doubling PRG, you will not get that. You get something completely random. In fact, you don't want this. You want, because something, a step here basically states that everything is equal except at this random location. And at this random location, it XORs to something random. But you don't want something random, but you want something meaningful. And there is a notion of a final correction word, which turns the something random at this leaf, at this target leaf, into whatever you're looking for. So the way DPFs work at a high level is that you have this, you construct these binary trees with length doubling PRGs, and then you have a notion of these correction words from login correction words at each layer of the tree, which turn this tree into something like this till the last layer, where everything is equal, like all the corresponding nodes are equal, except the target index, which to which you want to make a query. And then you have a final correction word, which basically turns this random value at the target into the value that you're looking for. So the way this part works of turning a tree which looked like this into a tree which looked like this, I'll be talking about just a few slides later. But the main idea is that you have a correction word at each layer, which re-randomizes one of the children and equalizes the other children. And once you've equalized one of the children, the length doubling PRG property would make sure that the corresponding children are again of the two trees remain equal. And then you have to correct one of, like, for example, you have to correct over here, and then you use the correction word. But the main thing that we'll be focusing on for this part of this part is that you come to this point where you have to the last place, to the last layer, where you have constructed a tree where all the leaf layers, like all the leaves of the two parties XOR to 0, except at the target location where they XOR to something random. And then you have the final correction word, which turned this something random into something you're looking for. And what we were looking for was M, as we had stated earlier. But now there is a now let's recall the problem. Now let's recall the problem that we were having. So now we want a case. So our goal is to write a value M into into the iStart location. The problem though is that the client who is sending these DPFs does not know the value M. And the reason they do not know the value M is because the value M was an intermediate calculation of the collaborative filtering algorithm. So just to go back to this slide, so this is the value that we are trying to write. And this value is something that the user who is downloading from the database has no idea about. This is the value the parties know, but the parties only know the shares of it. So they don't know this value in the clear. So the user can send them the DPFs at the correct location, iStart, but the user cannot send them the final correction word, which would turn the random thing into the value they're looking for. So that is the problem at hand. So the problem is that you don't know this value because this is an intermediate value that came up during the collaborative filtering algorithm, and actually nobody knows this value in the clear because the servers have been working in MPC and they only know the shares of it. So what we have, the situation we have is that we have P0 and P1. They know M0 and M1. They want to write M into a particular database. You have a client who knows iStart. So that is, they know where they want to write, and now they would like to perform this. So this is the main challenge. So the way we work around it is that we cut off the final correction layer for a moment. And now this seems completely useless because what you have is a DPF which basically XORs to something random at this location. But but what we do is that the client basically constructs a final correction word which would XOR to 0 at the target location also, but it sends the share of this final correction word to the two parties. So what do we mean? So it sends the DPF key and these correction words which allow them to construct the entire tree which looks something like this, which is equal everywhere. But as I said, it has something random over here and something unequal over here, but it sends T2 plus the shares of T2 plus R2. I mean, here we can plus and XOR can be taken interchangeably. And now the parties who have M0 and M1 do something very clever. They have got C0 and C1, which XOR to the reconstruction at the target. And now they exchange M0 and CW0 and M1 plus CW0, and they get M plus CW. And now, if exactly one of these parties applies the final correction word at the target leaf, what you would be doing is that you would be you would be canceling out this random value, and you would be ending up with the value that you're looking for, which is M. And how practical is it? In order to test the practicality, we implemented Persona and ran it over Amazon EC2 servers, placed them in geographically distant locations to mimic the real world latency, and our results were very encouraging. For example, Netflix, for example, has really back of the envelope calculations, has 110 million subscribers worldwide. The training is not sensitive to the number of users. And we could train 2 to the 15 queries on 2 to the 14 items in a minute. And that amounts to around 47 million queries per server per day. And with the current cost of EC2 servers, with a very small premium, we noticed that we could actually, if the entire if we scale it, Netflix could train on 100% of their data for just a very small premium. Yeah. So this concludes the first part of the talk. And yeah, I mean, if there are questions at this point, I would be happy to answer before I move on to the second part, which is the sender anonymous messaging systems.
Any questions? Okay, you can go on.
Sorry, I can go on?
Yeah, please go.
Oh, yeah. So the next part of the talk is about the broken promise of the internet, and we will take small baby steps in this direction. And the main technologies that we'll be using is zero knowledge proofs, disparate point functions, and again, secure MPC. So what is zero knowledge proof? A zero knowledge proof is that the prover wants to prove the knowledge of a statement to a verifier, and the goal is to prove the knowledge of the statement with the verifier learning nothing else but the fact that the prover knows the statement. The state of the art in sender anonymous messaging system is a system called Repost, which is an anonymous bulletin board. And Repost basically is a sender anonymous messaging system where you have a public bulletin board. The set of users are public. The set of messages is public, but who wrote what is private. So the relationship between the user and the messages is severed. And the way it works is that 2 servers hold a shared bulletin board, and after every epoch, they reconstruct their bulletin board, and we can think about this entire thing as an anonymous Twitter. So think about two databases. They have think about it in the following manner, where you have D0 and D1, which XOR to the bulletin board D. And the way you would write into a Repost system, suppose our entire bulletin board was a 1-bit bulletin board, and you want to write bit 1 at the LS location, at the X location. What you would do is that you would construct DPFs with the value 1 at location X and send these DPFs to the 2 servers, and they basically XOR the evaluation of the DPFs into their respective shares of the bulletin board. And of course, with the DPF property, that eval full of DPF0 and DPF1 is the standard basis vector at X, you would have written 1 in the desired location. Now, this has several problems. One of the problems is that a malicious client can send bogus DPFs and corrupt the entire database, because eval full of a bogus DPF and eval full of other bogus DPF would XOR to something completely random, not a standard basis vector, which would mean that your entire database would be corrupted. And in order to do that, a Repost, which used a zero knowledge proof to protect against malicious clients and basically clients who submitted these DPFs who wanted to write in a location basically had to prove that these are indeed DPF keys and not something completely random, while not revealing anything about the DPF key. However, Riposte used a less efficient version of DPFs, which is the square root n size DPFs, as opposed to the most efficient, which are log n size. And the reason that they did it is because it simplified their zero knowledge proofs. Then came next an improvement on it, and which was called Express. And Express modeled themselves on Riposte, and they in fact used log n size DPFs. So, but they worked in a slightly different model, which is a mailbox model of sender anonymous messaging systems. If you recall, Riposte was a public bulletin board where anybody could post anything on this public bulletin board, while as I said, the messages would be public. You would not know who wrote what. Express worked in a slightly different setting, where you have several mailboxes, and we can think about this use case as whistleblowers and journalists, and somebody who's expecting a message can register themselves with a mailbox. And these are 128-bit mailboxes IDs, and suppose these are the registered mailboxes. And now somebody and a writer, which you can think about as a whistleblower who wants to send some information to one of the journalists. They would know the mailbox ID of this journalist who would have communicated to them via some private channel. And they basically send huge DPFs of size 2 to the 128, but the Express server doesn't need to evaluate the entire DPF over the whole domain of 2 to the 128, but they evaluate it over only the registered mailboxes, and you add it and you add them up, and of course, again by the DPF property, you would be writing the message into the desired mailbox. The reason for having these large mailbox IDs is essentially that you don't want anyone to corrupt corrupt the mailboxes. That is, you don't want anyone to write into a mailbox without them knowing the mailbox ID. And having these large mailbox IDs basically prevents a malicious client from guessing some mailbox ID and clobbering the mailbox of an honest journalist. So Express's audit protocol also need an audit protocol because you want to check if these are actual DPFs and they don't corrupt the database. The way it worked is that they evaluated the DPF and then they checked if these are shares of a standard basis vector. At the first glance, this doesn't really seem like a problem because in order to write, you anyway need to evaluate the DPFs. So what's the big problem if you want to evaluate if you have to evaluate the DPF before you can reject it? But the problem is that a malicious client can subject Express to a denial of service attack, where it just keeps sending random DPFs which are valid or invalid, but it keeps sending them, and you have to keep expanding these DPFs before you can actually tell whether it is correct or not, whether it is something that is acceptable or not, thus the work that this malicious client would do is much lesser, because creating these DPFs can happen. Creating these random DPFs can happen quite quickly because you can just you just need to pick a random seed and random correction words. However, evaluating this entire DPF is O of n work, and thus the time to do rejection is much more. And that is where that is where our innovation was. That is, we came up with a protocol where you don't need to actually evaluate the DPF before rejecting it. So thus there was an exponential time improvement, and our system, which we called Sabre, took only O of log n time to reject a DPF, whereas Express took O of n time, which was the state of the art. How did it work? And so, and this is where a part of the discussion which I left earlier about the correction words and how we turned this random tree into something like this comes into picture. So as we recall again from the DPF construction, you have this length doubling PRG to construct a random tree, and then you use correction words to turn this random tree into a tree which looks something like this, where all the corresponding nodes in the leaf are equal except at the target leaf. The way it works level by level is as follows. At each level, we have a correction word, and this correction word is so designed that it turns one of the children. So you start with a root and you expand it and you get two random children. Now you use a correction word to turn one of these random children equal to each other in the two trees while re-randomizing the other one. So now, for example, here you want to say equalize the right child. So the correction word is chosen as T1 XOR with R1, and only one of these servers will apply the correction word to its children. Say this one did. So the left child is re-randomized to something new, but the right child is equalized to what was earlier. And now you expand it. Now with the length doubling PRG property, these two children are equal to these two, but you still have unequal children on the left side. But we use the same technique of using a correction word, which basically transforms one of these children, and exactly one of the parties will apply the correction word, and we keep doing it recursively until we get to something like this. Now we observe something already, that is a DPF key is valid if there is one colored path which starts from the root to the leaf, right? So there has to be a case that is, so, and what do we mean by a colored path? At each layer, you want something like this. You want the tree to look either like this. That is, one of the children should be equal and the other should be unequal. So this is a very important property which defines what a DPF is. So rather than, the earlier notion of what a DPF is, how we defined it was that you expand it, and if the expansion XORs to a standard basis vector, yes, it is a DPF. But with this but by looking at the way it is constructed in this setting, what we notice is that we have another way to identify what a DPF is. The way to identify is that you look at each layer, and at each layer, you start from the root, and you essentially check if one of the two children is equal or not. If one of the two children is equal, you leave out the equal child and look at the unequal child, and expand and check if exactly one of these children of the unequal child is equal or not. If one of them is equal, once again you leave out the equal child and you check if the children of the unequal child are again one of them is equal or not. And now you suddenly, instead of expanding the entire DPF, all you need to do is to traverse this path from the root to the leaf. And the way we check it, of course, is use secure multi-party computation to essentially check if exactly one of the tree exhausts to 0 or not. And of course, we need to compute PRGs using insecure multi-party computation. Regular PRGs using standard encryption protocols like AES would be very expensive to do in MPC. That is why we used a low multiplicative depth PRG known as low MC. And so what we needed to do was have a PRG implementation in MPC and a conditional swap to basically check if exactly one of them is equal or not. And then basically we were able to solve one important problem, which is rejecting the DPFs without evaluating them. Are we done? But not exactly, right? Because we still really need these large DPFs, because recall that we had to have 2 to the 128 or some really large number of mailboxes. And the reason we needed such mailboxes was that you didn't want a malicious client to essentially guess that, okay, this is a mailbox of of a trusted journalist, and now I'll send something completely garbage into it and corrupt whatever important information they have. But is it possible? The question is it possible to eliminate that? Can we use smaller DPFs, and can we eliminate the need to have such large mailbox IDs? And the answer is yes. And the way we did, and the main technique again we used is the fact that we are using the PRG evaluation using LOMC is very much MPC friendly. And the way we worked this out is that every so if we have, say, we have S mailboxes, every mailbox ID is simply the encryption in LOMC with a secret key of that mailbox ID. So you, if you're looking at mailbox ID I, the mailbox ID is the encryption of the LOMC encryption of E of I under some secret key. And whenever you register with a mailbox, you get this particular encryption. And now the person who is writing, the person who is writing this basically will send shares of this encryption. And now because LOMC is so MPC friendly, they can check in MPC if they are indeed the shares of the correct index which they're claiming to be. And just to look at the results finally, we see that when all the mailboxes are good, that is, you have like they're actually valid DPFs being sent, they still perform better than Express. And the reason is that although the protocol almost is the same, we have the luxury of using much smaller DPFs. However, when we have a bunch of bad writes, that is malformed DPFs, our performance improves drastically, and it is not a wonder because we don't need to evaluate the DPFs at all to compare to reject bad writes. Yeah, the future direction is like the big goal is to achieve this Everest of privacy for all. And the questions that I'm interested in are, we have been, like, a lot of my talk so far has been had this huge assumption of non-collusion, which is a very strong assumption. At the same time, it gave really nice results. So it is both, it's very tempting to use it because it outperforms almost everything that is there in practice. So the question that I would like to ask is it possible to, for example, incentivize a non-collusion assumption? Then the question of using of considering distributed multi-point functions. There have been some previous work in this direction. However, they use DPFs as a black box in this work. And is there a way to kind of exploit the internal structures of DPFs in order to come up with distributed multi-point functions, where you have functions which evaluate to 0 at every point, except a few, except a set of points where they don't evaluate to 0. And this would be extremely useful if you want to, for example, do multiple writes in parallel if you already know the indices of these locations. Like the other project that I'm interested in, and we're still and it is a work which will start soon, is DPF-based oblivious data structures, and in particular, our plan is to construct oblivious heaps using DPFs in a distributed setting. And how about and then the other things would be that I'm interested in is you see this, despite all the privacy enhancing technologies that we applied, for example, on our recommendation system, there is something inherently leaking about the algorithm itself, right? Because you know what you downloaded, and based on that, you got some recommendations. Now that itself leaks some information about what your peers must have seen, what your core Netflix subscribers would have watched, because based on because you downloaded something and you got some recommendations, and this information itself gives some idea about it. So that there is an inherent leakage in the algorithm itself, which can't be avoided by the privacy enhancing technologies that we use, like secure MPC. Is it possible to avoid that leakage? And does differential privacy help there, is a question that I would like to explore. And other things are systems like privacy preserving elections, auctions, and so on. And currently we have a submission of an ORAM protocol which works in 3 and 2 party settings. If you're aware of this CCS paper of LORAM, it is an improvement on that. And yeah, the main takeaways of my talk are that we discussed a sender anonymous messaging system named Saber, and a privacy preserving recommendation system named Persona. Persona worked in a 4-party setting, and Saber's main contribution was that we could audit these DPFs extremely fast, exponentially faster than the previous work, and that allowed us to avoid denial of service attacks. Yeah, that's my talk, and thank you so much for your attention.
Thanks, Aditya. Any questions, anyone? I had a couple of minor questions. So what is you mentioned the low MC PRG, which one, or is it something you designed, or is it an existing?
No, it is a very well-known PRG that has been used for whenever you want to whenever you want to have a PRG with fewer AND gates. Low MC is a great choice for it. Low MC is not a great choice if you are not doing MPC, because it is inherently slower than AES. However, in a secure MPC setting, low MC is much faster, because MPC, the multiplication of MPC is the main bottleneck in MPC. And the number of AND gates in low MC is much smaller than the number of AND gates in AES.
So what's the reference for this? So it's called low MC.
It is called low MC.
Okay. The other question was, I missed, probably went through it, to reduce the number of mailboxes, right? You're using a PRF, you mentioned this.
Yeah.
Maybe you could just go back to that. And
yeah, sure. So the main idea is that you rather than having this mailbox IDs which are random 2 to the 128 bit. So what we said is that we basically create, so our mailbox ID is the encryption of
when it's encryption, is PRF evaluation, right?
Yes, just a PRF evaluation of if it's a 5th registered mailbox, it is of 5, and now this is the mailbox ID. And now what you need to do is, now what happens is that you the client or when they register with the mailbox, they get this mailbox ID, and now the writer who wants to send a message to this mailbox ID needs to send the shares of this encryption E to the 2 servers, and also the shares of the index where they are writing. That is I0 and I1. So that I0, I1 add up to I, and the shares of the encryption. And now now the 2 servers can just use an MPC to verify that what they have got is equal or not. Like basically, they can verify that what they have received XORs to 0.
The DPF, the point is I or EKI?
Yeah. No. The DPF point is I. K is the encryption key, which is only known to this server.
Yeah, I was asking. So I thought the mailbox ID is this E, right? EKI. Don't you want the DPF to evaluate to M at EKI?
Yeah. So the DPF maps to I. So the DPF the DPF verification exists separately. At the same time, you want to check whether they know where they're writing to. Like it is like even just valid DPFs is not enough, right? Because you don't want a case where they're writing.
So you're not changing the writing to the mailbox part or DPF or anything. You're just saying those are used as an auxiliary proof that
Yes,
given this.
exactly.
Yeah. Okay. So it's
Exactly.
not like a kind of use like a signature on I that you're.
No.
A signature in the sense that it's a password or something, right? That you were given the ZKI, and my checking is by doing the PRF evaluation to
Right.
Yeah.
Right.
It's a Mac on. You could say it's a Mac on I. The
Yes.
ZKI is Mac on I.
Yes. You can say that.
Okay. Okay. All right. So yeah, if there are no other questions, and thanks for the great talk.
Thank you. Thank you for inviting.
I'll just close the recording. Oh. Sorry, it's a great one. Should have had. Let's see.
Is that the red button itself?
That will exit. Sorry, I'm just trying to. I could exit the meeting. That's fine. All right. So thanks, Adithya. Just
Thank you.
quit the meeting because I couldn't figure out how to close the.
Yeah.
Finish the record. Oh, I think the recording is still going on, and because the meeting is not over.
Oh, okay.
That's okay. We can snip it. So what I was going to say is that we'll put up the recording on our web page.
Yeah. Thanks. Yeah.
All right. So thanks.
Thank
bye.
you very much. Bye.